Hello everyone. So since we have completed chapter 13 in the previous video, and also since I was out and couldn't upload the videos, so what I'm planning to do is I'll make a WhatsApp group and I'll send the link to join the group in the chat itself. So in the description, so you are supposed to join it, and I'll be giving you the regular updates along with the important questions. So you can solve those questions and then I'll put up the solution and then we can discuss the other questions as well. And all the updates regarding the videos would be regarding the course would be updated in the group itself. So most probably in the link itself I'll share you the link for the group. Okay, now moving to chapter 14. This is the most important chapter of this unit. The name of the chapter is Further Topics in Linear Algebra. So in this, so you have done elementary row operations in the previous classes as well. Just revise all those topics. Now, in this chapter, our main focus from 14.3 onwards would be on condition for existence and uniqueness of solutions. You can expect questions coming from this. This is very important. It is highly expected questions would come from this. We'll discuss this as well. Now, starting with 14.1, linear independence. Firstly, if a system of equation is given to us, in this case we have three equations and three variables. So the three variables are x1, x2 and x3. The three equations are, so this we have already discussed how we can write this and the system as in vector form. So it is x1 where a1 is the vector, x2 a2 is the vector, x3 a3 and the right hand side b. So b, firstly a1 is 2 4 coefficients of x1, so it is 0 x1, so 2 4 0. Similarly for a2 it should be, you should, so I'm giving you a minute to fill this up. So for a2 it would be 2 0 6, and for a3 it would be -1 2 -3. For b, the right hand side is -3 8 and -12. So this can be written in this form. Now if you use Kramer's rule, you can solve the value of x1 x2 and x3. I'll solve for only one. So I'll tell you what the Kramer rule was. X1 was determinant of d1 upon determinant of a. So the A matrix as a whole is, okay, I'll ask you to solve itself. 2 2 -1 4 0 2 0 6 and -3. And d1 was replacing the first column of A with the B matrix, so it becomes -3 8 -12, then 2 0 6 -1 2 3. So determinant of x1 is determinant of d1 upon determinant of A. So just take 2 minute time to solve this. So try to expand this along with either this row or this column, because 0 है तो calculation easy हो जाएगी. Similarly A determinant इस column के through कर सकते हो, इस row के through, और इस column के या फिर इस row के through. So you will get some value of x1. So I'm giving you 2 minutes to solve this. Okay, so you need to revise the Kramer's rule as well, because it is also very important. Now x2 is coming to be half. Similarly, we can find the value of x2. x1 was coming to be half, and then the value of x3. So these are some numbers only. Suppose I'm not sure what the number of x2 would be, you can just put the value. Suppose it is coming out to be 0.1 and this is 0.2. Then we can say that b, the vector b is is linearly dependent on the vectors a, 2 and 3, because b can be written as a linear combination. So these are fixed coefficients, and since b can be expressed as a linear combination of the vectors, then we say b is linearly dependent on the vectors. Okay, now coming to the conclusion, what we have is the n vectors a1, a2, an in Rn are linearly dependent if there exists number. So these are numbers only, c1, c2, cn, not all 0, such that c1a1 plus c2a2 till plus cn an equals to 0. So the purpose is, if you have n vectors and you take numbers c1 a1 plus c2 a2, and if this is coming out to be 0, when at least one of them, one of the c1s, when at least one of the c1s is not 0, then we say the vectors are linearly dependent. Because in case suppose c1 and c2 are not 0, then we have c1 a1 plus c2 a2 equals to 0, then the vector a1 can be written as minus c2 upon c1 a2. So this can be written as a linear combination of this. So they are dependent. So in this case a1 is dependent on a2 when we assume that c1 is not equals to c2 is not equals to 0. When we assume c1 is not, when we assume c1 and c2 are not equals to 0. This is the specific case, and then we can see the one of the vector can be expressed as a linear combination of other. But in case if this equation holds only when, so if this equation holds only when c1 equals to c2 equals to cn equals to 0, when all of them are 0, then we say the vectors are linearly independent. I hope this was clear, because this is very important. So if this equation holds when c1, c2, cn equals to 0, only in this particular case, then we say they are linearly independent. And if this holds when c1, any of the c1 ci's is not equals to 0 and this equation still holds, then they are linearly dependent. Okay, now moving forward. Okay, you should try this. Prove that a1, the vector a1 is 3, 1 and a2 is 6, 2 are linearly dependent. Illustrate. So you need to show this graphically as well. So we know they would be linearly dependent if c1 a1 plus c2 a2 equals to 0 and c1 is not equals to 0 or c2 is not equals to 0. So in this case both of them would not be 0, then this is possible. Now firstly what we can see is, looking at a2 and a1, we can see is a2 is 2 times a1. So this gives us the fact that they are linearly dependent only. So what we have is 2a1 minus a2 equals to 0. So in this case this becomes c1, and so our equation was c1 a1 plus c2 a2 equals to 0. Comparing this with this thing, so c1 becomes 2, c2 becomes minus 1. And hence, if this equation is satisfied for c1 and c2 not equal to 0, then we say they are linearly dependent. So hence we have proved it. Now if you want to illustrate, a1, the first component 3, second component 1. a2 is, so this is a1, a2 is 6 and then 2. So this whole is a2 and till this point it is a1. So it can be expressed as a linear combination of the other. So they are linearly dependent. Now moving forward, the B part, you should try this. Prove that a1 equals to this and a2 equals to 1, 2 are linearly independent. So you know that this equation would hold true. This would be true when, to show that they are linearly independent, it should be the case that c1 equals to c2 equals to 0, and only in this particular case is this equation satisfied. So I'm giving you a minute to solve this. Okay, firstly, it can be written as c1 3 1 plus c2 1 2 equals to 0 0. So what we have is 3c1 plus c2 equals to 0 and c1 plus 2c2 equals to 0. Now you can use the substitution method. So c1 is coming out to be minus 2c2. With the help of this, we have 3 times minus 2c2 plus c2 equals to 0. So minus 5c2 is coming out to be 0 and c2 is coming out to be 0. Now if c2 is 0, put this into any of the equation or in this. So c1 is also coming out to be 0. Right? So in this case, this equation is satisfied only when c1 equals to c2 equals to 0. So we say that the vectors are linearly independent. Now if you want to illustrate this, a1 is 3 1. So 3 here, 1 here. This is vector a1. Now a2 is 1 2. So 1 here, 2 double the distance. This is a2. So they are independent. Okay. They are linearly independent. Okay, now moving forward. Any set of n vectors a1, a2 till an in Rm are linearly dependent if at least one of them can be written as a linear combination of the others. So same logic. c1 a1 plus c2 a2 plus cn an equals to 0. Now suppose c2 and c3 are not equal to 0 and other are equal to 0. So what we have is c2 a2 plus c3 a3 equals to 0. So c2 becomes, so a2 becomes minus c3 by c2 a3. So a2 can be written as a linear combination of this, and even if c1 is not equals to 0, then it would be minus c1 by c2 times a1. So this is the same thing. Now in this case, what we can see is the particular vector a3 can be written as a linear combination of it. So a1 and a2, so if we have t times a1 plus 1 minus t times a2, then as the value of t varies, it will span this whole of the area. So in this case, a3 can be written as this if it lies between it. So in this case, they are linearly dependent. Whereas if a1 is this and a2 is this, and for if t lies between 0 to 1, then we cannot express A3 as a linear combination of A1 and A2. And in that particular case, we say they are linearly independent. I hope this is clear. Okay, so now moving forward. Linear dependence and systems of linear equations. Firstly, we have m equations and n unknowns. The first equation, a11 x1 plus a12 x2 plus a1n xn equals to b1. Similarly, the mth equation would be am1 x1 am2 x2 plus amn xn equals to bm. So this implies x1 a1. So a1 is a column matrix of this thing. So a11 a21 till am1 plus x2. This is x2 and a2. a2 is this column matrix. So equals to b. This is the b is the right hand side column matrix. Now look at this proof very carefully. So suppose if we have two solutions to this system of equations, two solutions. Firstly, u1, u2, un and v1, v2, vn. Then they are the solution, which means if x1 equals to u1 and x2 equals to u2 and xn equals to un, then this system of equation would be solved. And similarly, if x1 equals to v1, x2 equals to v2 and xn equals to vn, then also the system of equation would be solved. Now u1 a1 plus u2 a2 plus un bn equals to un an equals to b. If u1 is a solution, similarly if the vector v is a solution, we get this equation. So mark this as a, marking this as b. Now subtracting the equation b from a, subtracting this from this, we have u1 minus v1 a1 plus u2 minus v2 a2 plus un minus vn an. So far this is basic calculations only. Now let c1 equals to u1 minus v1. So this becomes c1, this becomes c2 and this becomes cn. So what we are finally getting is c1 a1 plus c2 a2 plus cn an equals to 0. Right? Now if we are assuming that the solutions are different, that is the solutions are different when u vector is not equals to the v vector. So basically u1 is not equals to v1 and any one of this would happen. un is not equals to vn. Any one of this would happen, so the vectors are not equal. And since if they are not equal, so basically the solutions are different, which means not all ci's are equal to 0. Had it been the case they were equal, then every ci would be 0. Now since they are not equal, so not all ci's are equal to 0. I have just shown. And if system has more than one solution, right? So we have assumed there were two solutions and the two solutions would be different if not all ci's are 0. Right? So this equation that we are getting, I'll mark it in red. This equation that we are getting, now we know that it would have two solutions when all ci's are not equal to 0. And in that particular case, what we can see is, then we have already discussed, then in that case if all ci's are not 0 and this equation holds, then they are linearly dependent. This is a proof. This was important and you can just replay it if you want. Okay, similarly, now if they are linearly dependent, we know more than one solution can exist. On the other hand, if the column vectors a1, a2, an are linearly independent. Now if they are linearly independent, we have plus c2 a2 plus cn an equals to 0 and c1 and all of them are 0 only, then we know that the system has at most one solution. So at most 1, it can be 0 or 1. Whereas if they are if they are linearly dependent, we know it has more than one solution if they are linearly dependent. Okay, I hope this was clear. Now I'll give you 2 minutes to prove this. It is 12:47, so till 12:49 you have 2 minutes to solve this. You need to prove that these vectors are linearly independent. So you know what you're supposed to do. C1 A1 plus C2 A2 plus Cn C3 A3 should be equals to 0. And if C1 equals to C2 equals to C3 equals to 0 is the only solution, then we have that the vectors are linearly independent. Okay, so till 12:50 I've given you the hint, so just try to solve this. Okay, so basically you can write it as C1 101 plus C2 210 plus C3 011 as 0 vector. So what we have is C1 plus 2C2 plus 0C3 equals to 0, then 0C1 plus C2 plus C3 equals to 0, then C1 plus C3 equals to 0. Now with the help of this equation we get C1 equals to minus C3. With the help of this equation we get C2 equals to minus C3. Now C1 plus 2C2. With the help, C1 is minus C3 and C2 is minus C3. So this would become minus C3 plus 2 times minus C3 equals to 0. So what we have is, we'll solve this, minus C3 minus 2C3 equals to 0. This gives us minus 3C3 equals to 0 and this gives us C3 equals to 0. Now C3 is 0, this would give us C1 equals to 0 and this would give us C2 equals to 0. So this is what we are getting. C1 equals to C2 equals to C3 equals to 0, and then this system of equation is getting the solution. So what we say is that the system, that these vectors are linearly independent. Okay, so in the description I'll share the link for the WhatsApp group and just get added to the group. I'll keep you posted. We'll complete the course for sure, because I'm getting a lot of messages on the YouTube as well as on Insta as well to just complete the course, to post the videos. But I'll be completing it. I'll be keeping you updated and share it among your friends as well. those who are in first year, that might be helpful for them as well. Okay, so in the next video I'll be discussing the rank of the matrix. Okay, thank you.